Are you serious about salivary secretions? Yes, I'm serious. You're serious? Well, no, I'm serious. Are you serious about being serious? Very interesting, isn't it? Well, the parotid glands, serous means basically watery. It's a $5 word for watery. We don't go to medical school just to say watery. Whereas the submandibular and sublingual glands are more thick, they're more mucousy. Now, I love saliva because it's a very, very interesting substance. First of all, what are the exemptions about saliva from the rest of the body in terms of secretions? It's the only place in the body where the sympathetic and parasympathetic situation are both going in the same direction. They're both increasing secretions. Now, parasympathetic does it more and sympathetic does it less, but it's the only place in the body where sympathetic and parasympathetic are both pushing in the same direction. Maybe parasympathetic greater volume, but they're both increasing secretions. The initial fluid formation at the acinus has a chloride pump. Nowhere else has a chloride pump. Now there's chloride exchanges. There's an anion exchange all over the place where bicarbs and chloride exchange. But an actual chloride pump, well, that's unusual. Chloride pumps is only in the salivary glands. And now the ducts modify that initial acinar secretion because what it does is they pull out chloride, and with pulling out the chloride, pulls out that sodium. So it gets less salty. Now, this is really important because it means that saliva is the only hypotonic secretion in the body. Hypotonic is so that you can have taste particles going out of your food and into you. If your saliva was hypertonic, you would have taste coming out of the saliva and going into the food. You have to be receptive, and that is based on having a hypotonic secretion. Here's a picture of a submandibular gland, and we're looking at the serous acinus and the excretory ducts. The mucinous acinus, well, the mucinous or mucus, they're interchangeable terms, mucus or mucinous. Basically, you can always tell that they're always lighter because it's more watery. Their storage, more like water. The excretory ducts modify saliva tremendously. By what kind of pump? A chloride pump. Pulls out chloride and salt comes in with it. Salivary secretions are both stimulated by parasympathetic and sympathetic. Sympathetic is less in quantity. That's why it seems like your mouth goes dry when you get nervous. What's different about the pumps? Well, there's lots of sodium, potassium, ATPases, but this is a chloride pump. When the chloride is pumped in, it also pulls in sodium with it. And in exchange for the chloride coming in, there's bicarb going out. That's why this is also the only high pH fluid in the GI tract. You see, there's a high pH of salivary secretions so that we can neutralize the acid that forms in your teeth. If your teeth are exposed to too much acid, all your teeth will rot out of your head. That's why people who are mouth breathers at night often get cavities. Because people have, say, obstruction of their nasal passages, get open mouths and they dry out and they get cavities. You know, adults shouldn't be getting new cavities. That's a kid thing. Why is an adult having new cavities? Mouth breather, dry. You have Sjogren's syndrome or Sicca syndrome and you dry. Mouth gets dry, you lose all your teeth. So you also need that saliva to simply blow off the dirt off your teeth. It acidifies, and if you have acidification, it melts your teeth. So you got to neutralize it with bicarb. And it also has immunoglobulins in it, IgA, to neutralize bad things from the outside world. Can you get HIV from kissing? You cannot, because you have IgA. It neutralizes things in your saliva. And the IgA, it neutralizes it and protects you. My goodness, if I could, I would get like an IgA hat to put on my head. I would protect myself from all the bad thoughts I have. I'm protected from all the evil because I got IgA in my hat. Of what is the saliva composed? The composition of salivary secretions. Well, it's hypotonic because salt is absorbed based on the chloride being absorbed. It's high in potassium because you notice that what you have is one cation in, one cation out. Sodium is reabsorbed and potassium goes out. Chloride is reabsorbed and bicarb goes out. So this is a basic solution to neutralize the acid in your teeth. It's hypotonic, so you can taste your food. And amylase, well, it's a very interesting thing. You see, you need the amylase to taste your food, but it's not essential for life. Step 1 likes that. I'd like for you to know, do you understand that salivary amylase is not essential for life? It may be essential to be fully alive. You taste your food, and also how do you dissolve communion wafers if you didn't have salivary amylase? Dissolves communion wafers. There you go. Now, saliva also has lipase. Did you know that? That's why bread and butter taste good, because there's salivary lipase, amylase and lipase, but they're not essential for life. Now, here's where we have some overlap with biochemistry. In biochemistry, you'll learn about pK. Amylase and lipase work best at a basic pH or an alkaline pH or an acid pH. Is it an acid or is it an alkaline? Amylase and lipase work best at a pH of 5. 5 and 6. They don't work best at the low pH. That's why they're destroyed in the stomach. So amylase and lipase need a basic pH to work. And that's why they have very short duration of action for salivary amylase, because what happens is they're destroyed as soon as they hit the stomach. Now, pepsinogen and pepsin in the stomach work at an acid pH, and it's inactivated when it hits the basic pH of the duodenum. So the salivary enzymes are inactivated in the stomach. The stomach enzymes are inactivated in the duodenum. So each is in its place, isn't it? Amylase breaks down some of the starch just so you can taste your food. And lipase breaks down some of the fat just so you can taste your food. But what does protein taste like? What does pure tofu taste like? Nothing. Pure protein tastes like nothing because we don't have a salivary protease. So pure protein doesn't taste like anything because we don't have a salivary protease. So amylase and lipase are in the saliva, not essential for life. No, you won't be dying because they get neutralized in the stomach acid. They don't live long, about 30 seconds. Only about 30 seconds, amylase and lipase. The mucus and glycoproteins are simply to lubricate the world, and the immunoglobulins are to be able to protect you from things. And lysozymes are to protect you things too. Lysozymes is like an acid that basically dissolves bad bacteria. Lysozyme. Immunoglobulins neutralizes bacteria and viruses, and so do lysozymes. They burn them up like a flamethrower. Gastric secretions, the epithelial cells, secrete a highly viscous alkaline fluid. And basically, that alkaline fluid protects the stomach lining. You see, the acid goes out into the lumen, and the alkaline stuff is so that it protects the cells. And that mucin and bicarbonate is on the lining. The alkaline is in the lining. You mean, is that why it's called alkaline? Because it's on the lining? No, not really, but if that works for you, that's fine. It's basically like SPF 3000 to protect your stomach against the acid. You know, gastric acid is about 4 million times. 4 million times more acid in the blood. 4 million, yeah. Because pH is a logarithmic scale. When you go from a pH of 6 to 7, that's 10 times, 10 times, when you're doing pH scales. So when you go from a pH from 7 to 1, that's 6 log points. That's 10 to the 6. That's a million. And a pH of 7.4, that means the stomach is 4 million times more acidy. Nonsteroidals decrease the mucin because nonsteroidals block prostaglandins. Prostaglandins make the mucin. Prostaglandins make the mucin. And that's a must-know question. See, the pH of the gastric gland is as low as 1. And that is basically, if you look at the blood, from a pH of 1 to a pH of 7, 6 points on a log scale, 10 to the 6th. That means it's a million times more acidy. To 7.4, that's 4 million. The mucin is made by prostaglandins, and nonsteroidals block the prostaglandins. Wow. What is the major stimulant to the production of acid? Stretch. What makes the mucin? Prostaglandins. But what makes the prostaglandins? Stretch. So the same stretch that makes the acid is the same stretch that makes the mucin. And you are given the ability to protect yourself from the same thing that causes the stress. So if you're given the burden, you are simultaneously given the ability to protect yourself from the burden. Very theological, don't you think? Oxyntic. Well, that's a fancy word for just saying acid producing. Oxyntic? Damn. Sounds special. Where is that? I don't know, but it's oxyntic. What does that mean? It makes acid. The parietal cells in your stomach make acid. They also make intrinsic factor. You see, B12 comes into the body on a sort of a F1 visa called the R protein from your saliva. It makes it through the stomach, and then you have pancreatic enzymes remove the R protein. It gets onto a green card called the intrinsic factor. Finally, citizenship is in the terminal ileum, where it finally gets absorbed and made permanent. So the R protein is in the saliva. Pancreatic enzymes remove the R protein, and it goes on to intrinsic factor. And then finally, the terminal ileum is finally fully absorbed. At the end of the day, if you don't need the acid, you don't need the mucus. If you don't need the mucus, you don't need the prostaglandins. If you don't need the pepsinogen, the chief cells make pepsinogen, but it's not essential for life, is it? It's not. So if you don't need pepsin, you don't need acid. If you don't need acid, you don't need mucus. If you don't need mucus, you don't need prostaglandins. Well, what do you need in the stomach at the end of the day? The answer is intrinsic factor. The only thing you truly need for life is intrinsic factor. Do you know what the word intrinsic literally means? Necessary for life. Without intrinsic factor, it's deadly. You die. It's deadly. Do you know what the word pernicious means, literally? Deadly. So chief cells make pepsinogen, and pepsinogen is converted into pepsin. Pepsin is not essential for life because it doesn't have that long a duration of contact. Remember, the things that are made and secreted in the stomach are neutralized by the basic environment of the duodenum. Pepsinogen is not essential for life because it has a short duration of contact. The amylase and lipase in the saliva are not essential for life because they have a short duration of contact. But everything out of the pancreas is essential for life. The mucous neck cells make both the mucus and the bicarb to protect the stomach. That's why when you vomit on an empty stomach, you can still vomit up some stuff. It's mucus. You can actually vomit that up. Isn't that interesting? Yes, it is. Now, you have to know each one of these to the marrow of its bones. Every single word on this slide is essential. Do you understand? Every word. Parietal cells makes acid. Intrinsic factor also goes with the B12. The chief cells make pepsinogen, but pepsinogen is not essential for life. The only thing essential for life is intrinsic factor. This is the big movable interior mandala of the world. You see that the stretch makes the acid, the stretch makes the mucus. And without either of them, you still live. That's why you can live on that PPI you're taking for the rest of your life, because you don't need the acid. So have a good time. You could be on it forever. Here, this slide puts together everything we just said to control the gastric acid secretion. Stretch makes acetylcholine. Stretch makes gastrin. Both of those will also stimulate the parietal cell. Now, why do the histamine blockers, ranitidine, famotidine, nizatidine, cimetidine, ranitidine, famotidine, nizatidine, cimetidine, ranitidine, famotidine, nizatidine, cimetidine? Remember that you don't need trade names for step 1 or complex 1. Trade names, manufacturer's names are not on step 1 or complex 1. You need to know generic names, and you don't need to know dosing. Why do histamine blockers work 2/3 of the time? Because it turns out that they potentiate the other two. Histamine blockers will therefore reduce 2/3 of the acid, but they work much faster. Now, the parasympathetic stimulation will also make gastrin-releasing peptide. The gastrin-releasing peptide stimulates the parietal cells. And this summarizes it also as saying that the acid, the fat, and the osmolality that go into the duodenum inhibit the stomach. Control of gastric acid secretion is the parietal cells is basically through acetylcholine. Part of it is just the sight and the smell of the food. This is the cephalic phase of things. There's about 1/3 of it or half of it. Histamine does it through local release. That's what local release means, paracrine. And gastrin secreted by gastrin releasing peptide. Now, this is one of the features of our books. One of the features of our books is that we'll do something in a picture and then do it in text in the next page. So if it looks like the text says one thing and then the picture says another, that's meaning that it repeats it. Yes, that's right. In other words, the text will say it and then it'll be the picture, or the picture then the text. And they should be recapitulating each other. Now, in response to low stomach pH, somatostatin will inhibit gastrin and reduce gastric acid secretion. Somatostatin inhibits everything. If it says stimulate, then somatostatin is not the answer. If it says stimulate, then somatostatin is not the answer. Somatostatin inhibits everything it comes in contact with. At the cellular level, carbonic anhydrase converts carbon dioxide into acid and bicarbonate. Now, this same carbonic anhydrase facility of formula is the same one that happens in the stomach. It's the same one that happens in your salivary glands. It's just in the opposite direction. It makes bicarb in salivary glands. And it's the same one that happens in your colon in response to aldosterone. That's why aldosterone works not only on your kidney, your colon, your salivary glands, and your sweat glands, all through the same mechanism. Parietal cells pull out carbon dioxide from the arterial blood, and therefore, if the question says, where is the highest pH of any blood in the body? The highest pH of any blood in the body is the gastric veins. The highest pH of any blood in the body is the gastric veins. Or they can say, let's take a sample, and they give you the sample of blood, which has a very high pH, and they say, where did we take it from? Ooh, and you say gastric veins. So both of those are two different ways of saying the same question. You can ask a question that goes, hey, where's the highest pH? Gastric veins. This blood is taken as a high pH. Where'd you find it? Gastric veins. Gastric veins. And in the pancreas, it's the opposite direction. In the pancreas, the pancreatic veins have the lowest pH. The stomach veins have the highest pH, and therefore we maintain homeostasis. Hydrogen ions are secreted by this hydrogen-potassium ATPase in the stomach, and the pumping of these hydrogen ions makes the intracellular bicarb and its gradient across the membrane, so it creates the net force for it pumping chloride into the cell. But the bottom line is, the stomach is extremely acid, so the veins are extremely basic. The product is acid, the veins are basic. And in the pancreas, the product is basic, so the veins are acidy. So chloride is going to diffuse through channels across the apical membrane, and it creates a negative potential in the stomach lumen. And compared with extracellular fluid, gastric secretions are both high not just in acid, but in potassium and chloride as well. That's why it's hydrochloric acid. Oh, hydrochloric acid. Oh. And at the greater the secretion rate, the higher the acid and the lower the sodium. Yeah. And that's why vomiting produces metabolic alkalosis, because if you're vomiting out all the acid, your blood becomes basic. If you're vomiting out all the acid, your blood becomes basic because you got rid of all the acid. Now, you get low potassium for two reasons. Number one, gastric secretions are very high in potassium, so if you vomit them up, you lose a lot of potassium. The other part of this is, what happens to your blood potassium level when your blood becomes basic? You have a transcellular shift, and you have more potassium going into cells. So metabolic alkalosis results in a transcellular shift, lowering potassium even more. This picture summarizes it up. And it says the arterial blood is giving up carbon dioxide. The carbon dioxide is converted by carbonic anhydrase into bicarb, which goes back into the venous blood, and into hydrogen ions, which goes out into the stomach. Now, step 1 is very big on you knowing where the ATP is split. So it is not a small thing that you know that ATP is split not on the blood end, but on the luminal end. Now that's different than, say, a kidney. See, in secondary active transport, the ATP is split on the blood end, not on the lumen end. So here, the ATP is split on the luminal end where the stomach is. There are very few ATPases in the body. There's sodium-potassium ATPase all over the place. But one of the only places that has a hydrogen-potassium ATPase is the stomach. What's the other ATPase around the body? Calcium ATPase into the sarcoplasmic endoplasmic reticulum. Calcium ATPase into the sarcoplasmic endoplasmic reticulum to pump the calcium back in. So this summarizes everything together. Carbon dioxide out of arterial blood, bicarb into the venous blood.